So now that we've got this formula for the arc length of a curve, we're going to look at some examples and see how we can use this thing. Right. So first, I want to find the arc length defined by this curve between 1 and 3. Right. Very straightforward question. So to use our formula over here, I need to start by finding y prime, so I can square it and substitute it into that. So y prime that's going to be 3x squared. 3 over 12 is 1/4. So this will be x squared over 4 minus 1 over x squared. All right, we're going to square that and add 1 to it. So let's go to the formula over here. This is the integral from 1 to 4 of the square root of 1 plus this kind of weird expression here, x squared over 4 minus 1 over x squared dx. Okay, so let's see what we can make of this. Right? Let's multiply this out. This is the integral from 1 to 4 of the square root of 1 plus, it's going to be x to the 4th over 16 minus, when I multiply these two together, I get 1/4. So it's twice that. It'll be 1/2 plus 1 over x to the 4th dx. All right, so let's put the 1 and the 1/2 together. This is the integral from 1 to 4 square root of x to the 4th over 16 plus 1/2 plus 1 over x to the 4th dx. Now, it may not be immediately obvious to you, but you can check this. This thing actually factors here. This is the integral from 1 to 4 of the square root of x squared over 4 plus 1 over x squared dx. Right? Try multiplying that out, and you'll see that it does come to that expression under the previous square root. So now, the square root and the square, they go away. And this becomes the integral from 1 to 4 of x squared over 4 plus 1 over x squared dx. And we can do this integral. This is the integral of x to the 3rd over 12 minus 1 over x evaluated from 1 to 4. I'll put these numbers in. This is 4 to the 3rd over 12 minus 1/4 minus 1/12. I'm putting 1 in now. 1/12 minus 1. So this is what? 4 to the 3rd. That's 64 times, that's 64 over 12 minus 1/4 minus 1/12 minus 1. And now I need some common denominators, which is why I didn't reduce that first fraction. This is 64 twelfths minus 3 twelfths minus, well, careful, there should be a plus 1 here when we distribute the negative sign, minus 1/12 plus 12 twelfths. Right, now I can put all these things together. This is 72 twelfths, which is 6. Right there, excuse me. And there you go. There's our final value for the arc length of this curve between 1 and 4. Because we've got another example here. We're going to find the area, the length of the curve defined by this parabola. Right, very basic parabola. And this is going to be an interesting example for several reasons. First, it's going to let us use several of the integration techniques that we talked about in previous lectures. And it's going to illustrate the kind of situations that do come up with these arc length problems. So we're going to use our formula here, right? And so I'm going to start by needing y prime. So y prime is equal to 2x. Right, so that makes my formula here, this is going to be the integral from 0 to 3 of the square root of 1 plus 4x squared dx. And we've seen this kind of integral before, right? I'm going to do a trig substitution here. I'm going to let x equal the tangent of theta. So dx equals secant squared theta d theta. So let's make those substitutions. Excuse me, not tangent theta. This is going to be 1/2. I got to count for that 4. So this is going to be 1/2 tangent theta, and this will be 1/2 secant squared theta. All right, so let's make those substitutions. Then this becomes the integral from 0 to 3 of the square root of 1 plus 4 times 1/4 tangent squared theta. You see why I needed to have that 1/2 out there? Times dx, which is 1/2 secant squared theta d theta. Okay, good. So these 4's cancel, and all I have in there is 1 plus tangent squared, which is secant squared. And we take the square root of that, and it's just the secant. So I'm going to bring the 1/2 out in front, 1/2 integral 0 to 3, and I get a secant from the square root part here. Then I have this secant squared over here. All right, so this is going to be integral of secant cubed theta d theta. Now, the easiest way to approach this is to look at those reduction formulas that we talked about in an earlier lecture, right? And we have one for secant in theta. And the formula says, and I'm really going to write this out so you can see all the bits and pieces. This is 1/2 times secant to the 3 minus 2 theta tangent theta over 2. We're really going to have to keep track of all these 1/2s that end up in this thing. Plus 3 minus 2 over 3 minus 1 times the integral secant 3 minus 2 theta d theta. And I'm going to leave off on the limits of integration for just a little bit here until we get all these integrals straightened out. Then I'll stick them back in the end. Okay, so what do we have going on here? First, I'm going to go ahead and just do this part right now. This fraction here is 1/2. So I have a 1/2 there and a 1/2 here. I'm going to pull those out and make this 1/4 secant theta tangent theta plus the integral of secant theta d theta. Okay. Now what? I know what the integral of secant theta is. We worked that one out previously. So this is going to be 1/4 secant theta tangent theta plus the natural log of the absolute value of the secant of theta plus tangent of theta. And now I need to deal with those limits of integration, right? And I really don't want to have to try to take that back to being in terms of x instead of theta. So I'm just going to change the limits of integration. So what do I get to do when I'm doing that? When x equals 0, we get 0 equals 1/2 tangent of theta. That's tangent of theta equals 0. So theta equals 0. And on the other side, when we have x equals 3, 3 equals 1/2 tangent theta. Multiply both sides by 2, right? We get tangent theta equals 6, which means theta equals the inverse tangent of 6. So those are going to be my limits, and I'm really out of room here. So we're going to go from the inverse tangent of 6 on the top and 0 on the bottom. Okay, so let's do the substitutions here. This is 1/4 secant inverse tangent of 6 times the tangent of the inverse tangent of 6. That's just 6. Plus the natural log of the secant of the inverse tangent of 6 plus, again, the tangent of the inverse tangent. This is just going to be 6. Okay, minus, now here's where it's actually going to get nice. Secant 0, tangent 0, plus the natural log, absolute value, secant 0, plus tangent 0, close the bracket. All right, so I got to simplify that secant inverse tangent. And it's a trig thing, right? But we know how to do that. I'm going to draw a triangle here. I'm going to put an angle in here, and I need its tangent to be 6. So that's opposite over adjacent, which means from the Pythagorean theorem, the hypotenuse is the square root of 37. Okay, so what is the secant of this angle? Well, the cosine will be 1 over the square root of 37, which means the secant of theta is the square root of 37. Okay, and remember theta, the way I drew my triangle, theta is that inverse tangent. So the secant of the inverse tangent of 6 is the square root of 37. All right, so let's put these numbers in here. This is 1/4. That's secant tangent. This is 6 square root of 37 plus the natural log, absolute value, square root of 37 plus 6. Now, here's where it really does get nice. Secant of 0 is 1, tangent of 0 is 0. So both of these, so that term is 0, right? Excuse me. Put some parentheses here, so we're subtracting the whole thing. So this is minus 0 plus, and what happens here? Again, this is secant of 0 is 1, tangent of 0 is 0. That's 1, and the natural log of 1 is 0. So you see how that part turned out to be pretty nice in the end. So what's my final answer? Well, it's 6 square roots of 3 plus the natural log, the absolute value of the square root of 37 plus 6 all over 4. And that's it. Not the prettiest of answers, right? But that's where we're going to end up. All right, so like I said, there was a lot of interesting things going on here. We had to use trig substitution. We had to use a reduction formula. Then we had to do some work over here with the limits of integration from our trig substitution. And then we finally got our answer, which was a really kind of odd-looking number. But there it is. It's somewhere in the neighborhood of 9, right? So that's going to be our arc length. Okay, so the other thing that I wanted to take away from this is that this is not unusual. This is not the nicest of formulas to try to work with. When you've got a square root, and when you add 1 to the square of that derivative, adding 1, it kills a lot of the nice use substitutions you can maybe use. So this is not unusual with this kind of problem for them to get particularly messy before you get to the final result. So if you look back at both of the examples that we did in this lecture, you'll notice, I didn't explicitly mention this, but you'll notice that both of their derivatives are continuous on the interval that we were integrating over. You remember that was a requirement for using this particular arc length formula. All right, so what we're going to do in the next lecture is look at some examples where the derivative is not continuous on the interval that we're trying to find the length over, and look at some ways to handle that kind of situation.